Thanks, Dr. Leo. Okay, so that's a problem we have to deal with, right? The discriminator, the closer to optimality, the less gradient information, and we also need it to be close to optimality for us to train our generator properly. And then there's another issue with Jensen-Shannon that it has issues when you're working in a low-dimensional manifold support space, and we'll see more about that in a bit. So it might be enigmatic now, but we'll see more about it. Okay, so we saw that the main success of GANs comes from the choice of JS over KL divergence, right? So why not consider other distance measurements, and maybe we get some advantages over GANs by using a different distance measurement, just like GANs did with traditional generative models. So some of the distances we can look into will be listed here. Total variation is one of them, where you get the supremum or the max, or to simplify it, the max for this a subset of the support of the real distribution minus the generator and the generator distribution, and you want to find the maximum here, or the supremum, and that would be the total variation. KL and JS, we've seen them before, so I'm not going to talk about them here. And then we have the earth mover or Wasserstein. And spoiler alert, that's what WGANs will be using. And we'll see why in a bit. And the main intuition between earth mover is that the distance is the amount of energy, or the amount of mass that you have to move from the real distribution to the generator distribution in our case, so that they are equal. And it's called earth mover because you can think of it as, like, imagine that you have two piles of dirt. How many shovelfuls of dirt you have to move from the first one to the second one so that they look identical? And that's the intuition between the earth mover distance, or Wasserstein, as it's called. And you would need, so here pi of PR and PG is the set of all joint distributions. Or we could, I think, look at them as some sort of transport strategy, like how would you transfer dirt from the first one to the second one? And we want the optimal transport strategy, right? That would give us the minimum amount of mass that you have to move to the second one to make them equal, and that would be the earth mover distance. So earlier I mentioned low-dimensional manifold support. So let's look more into that and see how each of our measurement metrics that I just introduced perform in such a scenario, and why the scenario is actually prevalent. So real-world data sets can appear to be to have artificially high dimension. For example, you see all these images, and they are very high dimensional, but they just appear high dimensional because a lot of real-world images have to follow many different restrictions. For example, if you have images of dogs, then you know that it has to have 2 eyes, 2 ears, and so on and so forth. So it has some restrictions under the hood that it has to follow, and it can't have just a free-form high dimensionality. So yeah, under the hood, it's a lot lower dimensional than what it appears to be. And then if you look at the distribution for our generator, it's sorry, I'm seeing some questions here. Like TV. In practice, how do you get out the catch-22 situation with the gradient magnitudes? I don't understand the question. What is catch-22?
Oh, sorry. This is with the issue where you had to where you had to train the discriminator to high accuracy or low loss before you can start training the generator. But then again, you mentioned the gradients go to 0, so you don't have a lot of signals between the generator. I was wondering how you can handle that in practice.
Mm-hmm. I think. Sorry, I think. Oh yeah. Okay. Exactly. This problem makes GANs very, very hard to train, and you get very unstable training. So you have to be very, very careful with, like, how many steps are you going to train your discriminator before training a generator, and so on and so forth, and a lot of the other hyperparameters the GANs may have. So this would give you a very, very unstable training, and that's why training GANs is very challenging. This is one of the reasons. And WGANs is actually trying to address that problem by using a different measurement distance metric, as we'll see in a bit, on how that actually fixes the instability issue or makes it better. It's not going to fix it altogether. But okay, back to our discussion. Sorry that I read the chats late. I'm not used to, like, I'm not a prop. I'm not used to monitoring the chat as well. Okay, so the generator distribution, yeah, that also looks more high dimensional than it actually is. So you see that your generator is generating images. So you might imagine, oh, that's a very high dimensional space that we have. But your generator, if you remember again from last week for GANs, it's starting by sampling from a latent space. For example, this can be a vector of 100 elements, right? That was our Z noise. So again, under the hood, it's coming from a low dimensional space. So yeah, so we could imagine that a lot of the problems we have to deal with have this low dimensional manifold support. And sorry. And in such cases where PR and PG are in this low dimensional manifold support, have low dimensional manifold support, it is very likely for them to have disjoint supports, right? Imagine you're in a 3D space and you have two lines. It's very likely, it's not very likely for them to exactly match, right? But it's a lot more likely for them to be just somewhere in the space, or maybe have one intersection, right? Or if you have two planes, they might intersect in one line, but it's very unlikely for them to align exactly, right? So again, they will have disjoint supports. And to understand how each of our measurement techniques actually work in such a scenario, let's look at one example. So we have a 2D space here, and our real distribution is concentrated on the y-axis, and on the y-axis it has a uniform distribution. So x would always be 0 for it, and it only has support over 0 to 1 on the y-axis. And let's say our generator model has only one parameter, theta, and that determines where on the x-axis it is. And for the y-axis, it's similar to the real distribution. It's a uniform from 0 to 1. And based on the value of theta, again, this could move along the x-axis, right? It could be exactly aligned with the real one, or it cannot be aligned. So let's see what happens with each of our measurements metrics, the distance metrics. So for the total variation, sorry, Sanjana, I think you're, yeah, thank you. So yeah, we will have two scenarios, right? When theta is 0 and these two match exactly, when theta is not 0 and these are disjoint. And we can see that they have a disjoint support in this case. So what is the probability of, let's say A is any point here? What is the probability of that point? It would be 1, right? So it's here. The subset from 0 to 1, what's the probability of that on the y-axis? It's 1. So this would be 1. And for the generator, all the points are here, not here. So that would be 0. So that means our total variation when theta is not equal to 0 would just be 1 minus 0. But if it is equal, then it's just 0. I think that makes sense. For the Kullback-Leibler divergence, if theta is 0 and these two are exactly the same, KL divergence is 0. But if it's not 0, if they are not on the y-axis both, then PG would be 0, and this whole thing will go to infinity. And again, that's one of the issues we saw previously as well for the KL divergence. In that case, it was not as extreme as going to infinity, but we saw that it was quickly growing when generator distribution was going to 0, but QX was not 0. But PX was not 0, sorry, the real distribution. So for Jensen-Shannon, we don't have this infinity issue anymore, but it's still not perfect. When theta is equal to 0, we get 0. When theta is not equal to 0, we get log 2. And this is just a constant value. So two things I would like to I would like you to get out of this is that, first of all, these are not continuous, right? So at 0, none of them are continuous. And here we're just getting a constant value. We'll see why that's important in a bit. But for Earth mover, the amount that we have to move the real distribution to get to the generated distribution, you can see that that would be just the absolute value of theta in the simplistic case. It's continuous, and it has different values based on how far from the real distribution PG is, or generated distribution. So I think we can already see some benefits here when we're dealing with neural nets and how important continuity is, or to be differentiable, and for those gradients to actually mean something. Because if you have a constant value, then your gradient is just 0. It doesn't help you at all. So let's actually visualize that. For Jensen-Shannon, we get the plot at the top. We have a discontinuity at 0, and everywhere else, just a constant value, where the gradient is just 0. But that's not the case for Earth mover. So it's not a constant value. You have gradient information. It's continuous. Well, I think the gradient doesn't work at this point, right? It's not defined, but it's still a lot better than JS or callback Liebler, right? And this is where the math comes in that I don't delve into. So the paper proves, it's very simple to just say, the paper proves that if G is continuous with respect to its parameters theta, the Wasserstein loss is also continuous.